Welcome to the classified overview of Project Bellum Lenticularis, the Marquis-shaped lenticular saucer designed for advanced gravity modulation and multi-environment deployment. This aerospace platform leverages cutting-edge physics, including the Olzhoffen effect, Casimir compression, and harmonic plasma field modulation, to achieve unprecedented maneuverability in sea, land, sky, and space. In this series, we'll break down the core principles, system architectures, and operational logic that make this craft possible. Let's begin by exploring the foundational science and the unique bellows effect that allows the saucer to seemingly skip across spacetime, defying conventional propulsion and gravity. At the heart of the saucer's operation is gravity modulation via spin alignment and vacuum field tapering. The Olzhoffen effect uses dynamic nuclear polarization, aligning nuclear spins with microwave pulses and magnetic fields to reduce inertial mass. Casimir compression creates negative energy density between nanogap plates, generating localized spacetime curvature and zero-point lift. Plasma harmonic modulation, meanwhile, enables shielding, lift, and inertial dampening by interacting with the craft's shape and field geometry. These principles are not just theoretical, they're grounded in modern research and advanced materials science, forming the backbone of the saucer's propulsion and defense systems. Mathematics behind the saucer's operation is as elegant as it is powerful. Mass reduction is achieved through dynamic nuclear polarization, where the effective mass is a function of spin polarization. Casimir force calculations determine the negative energy zones between plates, while plasma frequency modulation is tuned to the electron density and field environment. These equations are not just for show, they guide the engineering of each subsystem, ensuring that every component works in harmony to achieve gravity reduction, zero-point lift, and stable flight across all environments. Project Bellum Lenticularis is built around a modular system architecture. The gravitational modulation core, GMC, uses DMP spin alignment and microwave pulses for mass reduction. The Casimir compression chamber, CCC, generates negative energy zones for lift. The plasma harmonic envelope, PHE, provides shielding and inertial dampening, while the temporal coherence system, TCS, maintains time stability. Structural hull materials like graphene titanium nanolattice and boron nitride shells provide strength and electromagnetic shielding. Each system is designed for adaptability, allowing the saucer to operate seamlessly in sea, land, sky, and space. Saucer's effectiveness comes from its ability to decouple mass from gravity using spin alignment, create localized spacetime curvature with Casimir compression, and dynamically shield itself with plasma harmonics. Time crystals stabilize temporal drift, enabling coherent movement even at relativistic speeds. Diamagnetic bubbles redirect gravitational flux, reducing drag and enhancing stealth. These innovations are supported by advanced materials and quantum field control, making the saucer not just a theoretical marvel, but a practical platform for multi-environment missions. Deep ocean deployment, the saucer's graphene titanium nanolattice hull resists pressure and maintains conductivity. Boron nitride shells provide radiation shielding, while aerogel-infused titanium foam buffers shock and thermal gradients. Photonic crystal arrays adapt to water's refractive index, cloaking the craft from sonar and bioluminescent detection. The plasma harmonic envelope is tuned for underwater harmonics, and the gravitational modulation core reduces effective mass for buoyancy control. Casimir compression and diamagnetic bubbles further enhance stealth and maneuverability, allowing the saucer to glide silently through the ocean depths. Field dynamics in the oceanic environment are a symphony of advanced physics. Casimir vacuum compression fields radiate as golden arcs from the hull, while blue and orange swirls represent the plasma harmonic envelope. Red arrows indicate diamagnetic field tunneling into ocean layers, and photonic cloaking currents shimmer along the hull's perimeter. The environmental context includes bioluminescent marine life and sonar shimmer, all interacting with the saucer's adaptive field systems to ensure stealth and operational superiority beneath the waves. Land, the saucer's hull resists thermal gradients and electromagnetic interference, while aerogel-infused titanium foam absorbs shocks from terrain impact. The lenticular geometry is optimized for atmospheric lift and refractive diffusion, with shape memory alloys adapting to terrain contours. Photonic crystal arrays provide stealth against optical and infrared detection, modulating refractive shimmer to cloak the craft in dust-heavy environments. The gravitational modulation core and Casimir compression chamber work together to enable hover and lift, while plasma harmonics shield against wind, dust, and heat. On the ground, the saucer's field dynamics are tailored for stealth and environmental adaptation. Red arrows depict the plasma harmonic envelope for shielding and lift, while orange arrows show secondary plasma sheaths modulating terrain interaction. Blue arrows represent diamagnetic field tunneling into soil and rock, and golden nodes highlight Casimir compression cores. Atmospheric refractive shimmer creates a wavy distortion above the saucer, blending it seamlessly into the landscape and masking its presence from detection. In the sky, the saucer's hull is engineered to withstand thermal gradients, electromagnetic interference, and atmospheric pressure shifts. The lenticular geometry provides aerodynamic lift, while shape memory alloys adapt to wind shear and altitude transitions. Photonic crystal arrays cloak the craft from radar, LiDAR, and optical detection, modulating refractive shimmer for stealth in clouds and sky layers. Gravitational modulation core and Casimir compression chamber stabilize altitude, while plasma harmonics and diamagnetic bubbles ensure smooth, shielded flight above mountainous terrain. Aerial deployment showcases the source's mastery of atmospheric physics. Red orange swirls represent the plasma harmonic envelope for shielding and lift, while burnt orange arrows show secondary plasma sheaths modulating altitude. Blue arrows indicate diamagnetic field tunneling into atmospheric layers, and golden nodes mark Casimir compression cores. Atmospheric refractive shimmer creates a wavy distortion above the saucer, blending it into the clouds and masking its presence from both ground and aerial observers. In space, the saucer's graphene titanium nanolattice hull resists cosmic radiation, micrometeoroid impact, and thermal extremes. Boron nitride shells provide dielectric shielding and quantum field insulation, while aerogel-infused titanium foam maintains internal equilibrium. Photonic crystal arrays cloak the craft from optical, infrared, and cosmic background detection. Gravitational modulation core and Casimir compression chamber enable zero-point lift and field stabilization, while plasma harmonics and diamagnetic bubbles protect against solar wind and cosmic particles. In the vacuum of space, the source's field dynamics are optimized for zero-point lift and cosmic shielding. Orange rings represent zero-point field modulation, while red plasma loops form the plasma harmonic envelope. Blue arcs show diamagnetic field deflection, and golden nodes highlight Casimir compression cores. Temporal stabilization is achieved with time crystal oscillators, and the environmental context includes Earth's curvature, starfields, and cosmic shimmer, all interacting with the source's advanced field systems. Subsystem overlay provides a photorealistic, near 3D view of the saucer in deep space. Each subsystem is clearly labeled. The gravitational modulation core glows blue at the center, Casimir compression cores are marked as golden nodes, and the plasma harmonic envelope swirls in red-orange around the hull. Time crystal oscillators and diamagnetic bubble generators are also highlighted, showing their roles in temporal stabilization and mass reduction. This overlay demonstrates how each system works together to ensure operational integrity in the harshest environments. Photorealistic internal cutaway reveals the source's core subsystems and energy flows. The gravitational modulation core sits at the center, surrounded by cryogenic superconductors. Casimir compression cores are embedded around the perimeter, while plasma ring conduits and M-field modulators weave through the mid-layer. The hull's outer layers are composed of graphene titanium nanolattice and boron nitride shells, with aerogel-infused titanium foam for thermal regulation. This cutaway shows how each layer and subsystem is integrated for maximum efficiency and resilience. Temporal overlay highlights the source's advanced time management systems. Time crystal oscillators maintain temporal coherence across relativistic gradients, while the gravitational modulation core and Casimir compression chamber ensure mass reduction and zero-point lift. Plasma harmonic rings and diamagnetic fields are visualized as swirling overlays, showing how the craft stabilizes causality and prevents decoherence. This overlay is crucial for missions involving high-speed maneuvers and deep space navigation. Mission Scroll presents subsystem glyphs and telemetry overlays in a photorealistic, near 3D format. Each glyph represents a core function: DMP spin coherence, Casimir compression, plasma harmonic shielding, temporal stabilization, mass field reduction, and photonic cloaking. Telemetry arcs show energy flow and field gradients, while operational directives outline zero-point field modulation, gravitational lensing control, and stealth dynamics. This scroll serves as a quick reference guide for mission planning and in-field adjustments. Spatial dimension diagram maps out subsystem placement zones and dimensional field gradients. The gravitational modulation core occupies the central chamber, while Casimir compression chambers and plasma rings are arranged around the hull. Temporal coherence systems form a base ring, and diamagnetic bubble generators are positioned for optimal mass field reduction. Dimensional overlays visualize zero-point field rings, plasma flows, and spintronic control grids, providing a comprehensive view of the source's internal zoning and spatial coherence. Source's resilience and adaptability stem from its advanced materials. YBCO superconductors enable magnetic field generation and spin alignment, while graphene and carbon nanotubes provide lightweight strength and conductivity. Boron nitride nanosheets offer radiation shielding and dielectric control, and aerogel titanium foam ensures thermal insulation and shock absorption. Photonic crystals are embedded for cloaking and field shaping, making the craft both robust and stealthy across all environments. Gravitational modulation core is the heart of the source's mass reduction system. Using dynamic nuclear polarization, it aligns nuclear spins with precision microwave pulses and cryogenic superconducting magnets. This process decouples the craft's mass from the gravitational field, enabling rapid changes in weight and inertia. The core is monitored by quantum sensors for real-time feedback, ensuring stable operation even during high-velocity maneuvers or environmental fluctuations. Casimir compression chamber generates negative energy zones by compressing the quantum vacuum between nanogap plates, This creates localized spacetime curvature, providing lift and field stabilization without traditional propulsion. Quantum pressure regulators maintain equilibrium, while field stabilizers ensure the chamber's effects are precisely controlled. The CCC is a key enabler for zero-point lift and advanced maneuverability in both atmospheric and space environments. Plasma harmonic envelope surrounds the saucer with toroidal plasma rings, tuned to specific frequency harmonics for each environment. These rings provide dynamic shielding, inertial dampening, and lift. M-field modulators shape the plasma envelope, adapting to turbulence, wind, or cosmic flux. The PHE is essential for both defense and propulsion, allowing the saucer to transition smoothly between sea, land, sky, and space. Temporal coherence system uses time crystal oscillators and chronofield stabilizers to maintain temporal integrity during high-speed maneuvers. Quantum dot feedback grids provide real-time telemetry, preventing relativistic drift and phase decoherence. This system is vital for missions that involve rapid acceleration, orbital transitions, or operations near strong gravitational fields, ensuring the crew and systems remain synchronized across all timeframes. Saucer's hull is a marvel of modern engineering, combining graphene titanium nanolattice for strength and conductivity, boron nitride for radiation shielding, and spintronic metamaterial layers for field control. Adaptive shape memory alloys allow the hull to change form in response to environmental pressures, while photonic crystal arrays enable stealth and refractive modulation. This multi-layered approach ensures both durability and adaptability in any operational context. Field tapering and shape modulation are achieved through the saucer's lenticular geometry and harmonic resonance nodes. Shape memory alloys allow the hull to adapt dynamically, enabling the bellows-like mass modulation that gives the craft its signature skipping motion. Harmonic resonance nodes fine-tune the field interactions, optimizing lift, stealth, and energy efficiency across all environments. Environmental interaction system manages external field interactions, cloaking, and environmental shielding. Diamagnetic bubble generators create magnetic repulsion zones, deflecting particles and reducing drag. Photonic crystal cloaking adapts the craft's appearance to its surroundings, while plasma sheath emitters provide dynamic shielding against high-velocity impacts and electromagnetic interference. This system ensures the saucer remains undetectable and resilient in any environment. Bellows effect is central to the saucer's unique motion. By synchronizing mass gain and reduction cycles with microwave pulses and Casimir cavity compression, the craft achieves a rhythmic, pump-like movement. Plasma harmonics act as both shielding and propulsion, tuned to resonate with subatomic particle frequencies. This interplay of fields and shape modulation allows the saucer to skip across spacetime, mimicking the motion of skipping stones across water. Project Bellum Lenticularis draws on research from leading institutions. Sandia National Labs contributes advanced spintronics and quantum materials, Los Alamos provides expertise in high-energy field manipulation and time crystal research, and China Lake specializes in electromagnetic propulsion and stealth composites. These collaborations ensure the saucer remains at the forefront of aerospace innovation, integrating the latest scientific breakthroughs into its design. Path to full deployment involves several key steps. Subsystem blueprinting defines each module, from the spin alignment core to the quantum sensors. Lab simulations test the effects of DMP on inertial mass, while material sourcing ensures access to aerospace-grade graphene, YBCO, and spintronic components. Field testing begins with small-scale levitation and mass reduction trials, gradually scaling up to full environment deployment. Each phase is meticulously documented to ensure operational readiness. With all systems integrated and tested, Project Bellum Lenticularis stands ready for multi-environment missions. Its modular architecture, advanced materials, and quantum field control make it a versatile platform for exploration, defense, and scientific research. As new discoveries emerge in quantum physics and materials science, the saucer's design will continue to evolve, pushing the boundaries of what's possible in aerospace technology. The future of gravity modulation and zero-point propulsion begins here.